Alright, so today we are going to look at motion graphs, more specifically distance time graphs. This is future Mrs. Beadle who wrote the ICANN and did the whole lesson already and realized it's really long, so we are actually going to go ahead and cross out our practice problem so I can explain a situation from a motion graph, specifically distance time graph, using focus notes and a teacher video. Let's go ahead and get started with setting up our notes. Alright, so here are our notes set up for today. We have a column for a graph, we have a column that is titled what it means, and we have a column titled example. We also have a spot for my example, Mrs. Beadle's example, which will draw a graph here and an example or an explanation, and then a practice problem where you'll draw the graph and the explanation here. I am going to have you pause this video, but before you do, if you have the ability to, if you wouldn't mind grabbing two colored either highlighters if you have them. If you don't have highlighters, colored pencils, markers, crayons, colored pens, something like that. It will help you kind of understand. I'm going to keep my notes color coordinated for you today as well. So if you have the ability to use those on top of whatever basic writing utensil you're using, that would be great. I went ahead and drew my two highlighter colors down here at the bottom. I'm going to use a blue and a green. So if you'd like to follow along with me, you can. Otherwise, go ahead and pause the video right here until you have your notes set up. So a really key point about motion graphs and the graphs that we're going to keep looking at is first of all the why. Why in the world are we even looking at graphs? And I really love this quote here. Describing the motion of an object is occasionally hard to do with words. Sometimes graphs help make motion easier to picture and therefore easier to understand. So really what we're trying to do is we're trying to take these big lengthy word problems and these things that really don't make sense written out and show them in a verbal way, or in a visual way that'll make it easier to understand what's going on. If you're not familiar with graphs and you're not very comfortable with them, this might be a little bit challenging, but we are going to get through this together. So there's a couple things I should mention. When we're going to be talking about motion graphs, there are a couple different names for that. So you can call them a motion graph. You can also call them distance time graphs. And you can call them position time graphs. From this point on, I'm going to pretty much be calling them distance time graphs. The reason why is because that is actually telling us already what our X and Y labels are. It's telling us what we're seeing across the graph. So we are comparing distance by time. A lot of the examples we'll look at today use position, but that is the same thing as distance. Notice they're still measuring in meters, which is our measurement for distance, and time in seconds. So distance time graph is what we are going to call them, but please know if you hear these things moving forward, they are talking about the same thing. So motion graph, distance time graph, and position time graph are all talking about the same thing. One other little disclaimer for you, or little heads up, is that some of these things might be very obvious and make a lot of sense, and then there's going to be some of these things that might be a little tricky because we're not just looking at how fast an object's going, we're actually looking at how it is moving. What is its distance from its starting point to its ending point? A lot of the stuff that you look at in math is a rate and its slope, and you're usually just looking at speed or that rate of movement. This one's going to be a little bit different, so please bear with me and pay a little bit of attention to some of those details that I'll point out for you. So the first distance time graph that we're going to look at are for objects at rest, meaning objects that are not moving. So I'm going to go ahead and set up my first little box. I'm going to draw in this example here as my graph. Okay. So go ahead, if you want to pause the video to draw that graph in, go ahead. And I'll show you my finished version at the end of this slide just so you get a feel for what it looks like. So this is where if you have that highlighter, you can go ahead and I'd like you to highlight that line, one of your colors. I'm consistently keeping objects at rest blue for us. So I just want you to highlight it so that you are aware then, and it's a reminder that this is all going to be the same thing. So what does this mean? Okay, so in my middle section, oops, that's still a highlighter. Okay. In this middle section, we're going to write what this means. So an object at rest means it's not moving. So I'm going to write not moving. An object at rest is not moving. That means that its distance or its position is not going to change. So distance will not change. So then let's see what this looks like. Now, that what I just wrote here, I'll highlight it for you again. What I just wrote here, that goes in that middle column of what does it mean. Okay. Now, let's see what this looks like before we try to write an example. So I have a little setup here of the little toy monster truck that you saw me struggle with at the beginning of our physics unit, and a meter stick. So I've just taken every mark on our graph here, and that was 10 centimeters for me. So I took the car and I noticed where it was, so 0 centimeters, 10, 20, 30 centimeters at rest. So let's see what this looks like. Super exciting, right? The car is sitting at rest, not moving, at that 30 centimeter mark. Okay. I want to do one more example just so you see this one, since this one is kind of common. So I have another graph down here. You don't have to draw this graph. I would just like you to pay attention to it. So this graph down at the bottom, I'm going to add my labels, distance and time. Okay. Now, a very common example is going to be this right here. So knowing what we know, it's a straight line. Ooh, we should probably add that to our notes. So up here, let's go ahead and add straight line. Okay. So it's a straight line. It's not moving. Its distance will not change. One other thing we might want to add, okay, to that middle column is actually part of a math term that we're going to talk about in a little bit, but its slope is 0. Okay. Like I said, we're going to come back to that in a little bit. This bottom graph down here, though, okay, I have a straight line going from 0 all the way over through my time in seconds. I'm going to know that it's not moving, and its distance won't change because it's a straight line and the slope is 0. Okay, so let's see what it looks like. Again, super exciting. So, objects at rest. We can go ahead and we're using one color to describe it, like I said, blue. We know that objects at rest are not moving and their distance won't change. And when we go to graph, we graph with a straight line with a slope of 0. Okay, for the last part of our notes, we need an example. I'm going to go ahead and use, this one up here as our example, since that's the graph that you guys have in your notes. Okay, so our example is going to be us verbally, or in this case, written, describing what's going on. So I'm going to watch the video again. Okay, super cool, super exciting. So what I am going to write for my example is the toy car, or monster truck, whatever you'd like to call it, was at 30 centimeters and did not move. Okay, so the toy car was at 30 centimeters and did not move. Another way we could say this would be that the toy car started at 30 centimeters and remained at rest. That's going to be the more scientific way to say it. I'm going to go ahead and write both in my notes for this first one, just so we're getting comfortable with the language of it. And then give me 1 second and I'll show you my notes. Okay, so here's my example notes. If you want to pause the video here to make sure that you've got everything down and you're kind of getting the hang of what this looks like and how it's set up, by all means. I'm not going to stop it after each one of the rest of after each one of the rest of these, I'll actually go ahead and wait until we do forward and backwards constant speed together, and then I'll stop it again at hybrid. Okay, so use this time to quick check, see if yours looks similar to mine. If it looks different, that's a-okay, as long as you're understanding how we're organizing our notes and our thinking today. Okay, so next up we're going to talk about objects moving with a constant speed. This is going in the same direction. This means that they have the same speed throughout. They're not accelerating. They're not increasing their speed. Their speed is constant, meaning staying the same. Go ahead and I'll write that up above our notes as well. Oops. Staying the same. Okay, so let's go ahead and take a minute to draw this first graph here into our next box. Forward at a constant speed is what I titled mine. So forward at a constant speed. And then I'm going to go ahead and once my box is drawn, I'm going to highlight that line so that I'm keeping those colors in my mind to help keep things together. Okay, go ahead and pause the video as you need it to copy that down. Okay, now that you've got that down, let's go ahead and talk about what this means. So one thing that this means is, I wanted to write in black. Okay, one thing this means is that the speed stays the same. That's kind of what we were saying when the word constant and what that means. But speed stays the same. Another thing that we need to note about this is that we are moving forward and away from the origin. So moving forward and away from the origin. Now remember, in math, I apologize for my terrible handwriting here. In math, the origin is this 0, 0 point right here at the middle. That's going to be kind of like our 0 centimeter mark on our video. So right there, that's going to be our origin. So we are moving away from that starting point or that beginning point. We don't actually call it a starting point though, because when we talk about starting point, we're talking about the object. Okay? So we want to make sure that we're using our correct math terms and we're moving forward away from the origin, or away from 0 centimeters would even work in our examples. So let's go ahead and see what this video shows us as it's showing us exactly what that graph is. So I'm seeing 10 centimeters here. Oh no, too many things. 10 centimeters is where we would start, and at a constant speed we're going to move forward 10, 20, 30, 40 centimeters. All right, let's go ahead and see what it looks like. So there's our 0, 0. Constant speed from 10 centimeters all the way over to 40 centimeters. So let's go ahead and describe that. So we can say the toy car started at 10 centimeters and moved at a constant speed forward to 40 centimeters. Now, I don't know if you caught that, but what we just said was its velocity, speed plus direction. We said it was moving at a constant speed forward in some direction. Okay? So our distance time graphs are actually showing us the velocity of objects. But let's not get too far ahead of ourselves. Let's go ahead and write that down in our notes. Again, it was the toy car started at 10 centimeters and moved forward at a constant speed to 40 centimeters. Okay, so we're going to go ahead and move to the next set of boxes, the third one down. And this one is actually going to still be a constant speed, but this one's actually going to be backwards at a constant speed. Okay, so I have my distance, time graph here. Again, I apologize for the really sad writing. I'm going to highlight it in my color. Looks like I need to fix my highlight colors. Back to green. All right. So go ahead again. If you need to pause a minute to get this drawn into your notes, go ahead. And here's what that graph is telling us. So what does it mean? It still means that the speed stays the same, right? We're still talking about constant speed. Speed stays the same. The difference here is that we're moving backwards towards that initial point or towards that beginning. In this case, it's not necessarily the origin, but it's back towards the time line, back towards that zero distance. So this is moving backwards. Looks like moving towards the zero, or our x-axis, that time line. Okay, so let's go ahead and watch the video and explain it with our example. So let's watch what happens. According to my graph, I should be able to start at the 10, 20, 30, 40 centimeter mark, and it should go backwards to 0. Let's see what happens. So let's write out what happened. The toy car, where did it start? At 40 centimeters. So the toy car started at 40 centimeters and moved backwards at a constant speed to the 0 centimeter mark. So now that we've looked at both of these, and again, pause the video if you need it, wherever you need it. Now that we've looked at both of these, we can actually start talking about how this works mathematically, just like we did with our graph at rest. So we can say, when we graph these, that an object with a constant speed moving forward has a positive slope, meaning that the graph looks like it's going up. So if you want to put in little parentheses to remind you what that means, up. And a backwards moving object with a constant speed, our slope, I'm going to have to move a little, our slope is negative, or to keep it consistent with the rest of them, we'll write negative slope. Negative slope, meaning that our line is going down. This is another really good way to remember it as you start working through the problems. Go ahead and give me a second and I will go ahead and show you what my notes look like for this. Okay, so here are my notes. You can see one thing I started to do is I realized as we're going through here that this part right here that reminds me what we're doing, I wanted to highlight that just to remind myself what we were talking about in each of those examples. So feel free to do the same. And if you are peeking down towards the bottom, you can see that the next one we're going to talk about is a hybrid. Before we get there, I just want to do a quick refresher on slope. This isn't something that you have to write down since it's something you've covered in math before. If you feel like you should write it down to help yourself out, by all means go ahead on a separate sheet of paper or in the corner kind of by where we're going to do my example. Okay, so let's talk about slope. Slope is a word that you've used before. Slope is a math word. Okay, we typically see it in math. That's the first place you've seen it this year. But it has to do with the rise over the run, or the steepness of our graph. This might make a lot of sense to you. So far we've just been talking about the direction. So in this graph here, number 1, I'm going to call it, we have a positive slope, and we can tell because we're moving this way, we've been talking about direction, so we're moving forward. In this one here, we can see we are also moving forward because our slope is positive. Turn that one into an A. And then this one here, graph number 3, we actually have a slope that goes down, a negative slope. That tells us we're moving backwards. Okay. The difference here, though, is these graphs also tell us a little bit about speed. So if you can imagine, let me get my pointer out. If you can imagine this graph right here, if you have race car number 1 or race car number 2, which one of these would you think would be the fastest? Take a minute in your head, think about what you would say and why you would say that. Okay, so if we look at the slope, this one has, I'll draw a slope triangle in here for you too. Okay, this slope here, I go up 2 over 4, up 2 over 4. That gives me a slope of rise over run, 2 over 4, simplified down to 1/2. Whereas this slope, I'm going to go ahead and go like this. It gives me a slope of 1, 1. So we can start to see that the slopes also equal to 1. Okay? The slope of a graph is going to tell you how fast or what the speed is. So if you're looking at just between 1 and 2, okay, just between these two graphs here, number 1 is actually faster because the line or the slope itself is steeper. Imagine if you had to ride a bicycle up that hill, okay? The tougher that hill would be to ride up, in comparison, that's going to be your steeper slope. Now, if we throw graph 3 here into the mix, I'll draw a slope triangle out for graph 3. So this one is going backwards, meaning it's going to have a negative slope, okay? But it is over 2, down 3. So rise would be 3 over 2, negative. Now, I know fractions aren't our favorite. They're not my favorite either. If we change this to a mixed number, something you might be more familiar with, our slope here is actually negative 1 and 1/2, meaning of the 3 of these graphs, the fastest one is actually graph 3. The steeper the slope, the faster the object is going, whether it's forwards or backwards. So again, this is just a quick little refresher. You don't have to write it down if you don't want. If you want to make a note at the top, steeper the slope equals faster the speed. By all means, I'm going to add that to the top of mine, just so I have that written down and committed to memory. But let's go ahead and look at a hybrid graph next. So a hybrid graph is exactly what it sounds like. It is a mixing of 2 different kinds of graphs. When I think of hybrids, one thing I usually think of is the liger, like the lion-tiger hybrid. So 2 things put together to make this one product. So I have an example distance time graph down here. I'll go ahead and take a minute to put that into your notes. Oops. There you go. Distance time. It doesn't have to be perfect, but you're going to want the general shape of it. So go ahead and take a minute, draw that in. And then let's go ahead and identify it. We have 2 different kinds. Let's identify each part. We have 2 different kinds of graphs that we've looked at. We've looked at objects at rest, which I've used as blue, which we know, going back into our notes, have a slope of 0, or they're straight, flat lines. Now, objects moving with a constant speed are also straight lines, but they have either a positive or a negative slope. So I'm going to go ahead and I'm going to highlight all the spots on this graph in my notes that are flat. So that's telling me every time I see a flat point, that object is at rest. And then I'm going to go ahead and take my second color, in this case green, and anything that's moving at a constant speed is going to get green on it. So this is the whole reason why I had us use a couple colors. It really shows these parts of the graph really well and lets us explain it a little better in words. So once you've got that down, let's go ahead and talk about what a hybrid graph means. We did a little bit at the beginning, but let's actually write some things down for it. So a hybrid graph has parts of many types. Of distance time graphs. All right, so it has many types of distance time graphs, many parts, of the different types of distance time graphs, and it's still showing motion over a time, like the rest of them. The difference is it's not going to be constant. So everything that we've done, the object at rest, that's constant. It's still at rest the whole time. The constant speed graphs, obviously, constant's in the name. That means it's consistently and only going one way. But these graphs show motion, but it's not constant motion. It's going to be different at different spots. So let's go ahead and see what this graph looks like before we write our example. So according to my graph, we should start at 0 centimeters. We should go up to 20 centimeters at a constant speed. We should sit there for a little while, remain at rest. Then it should go from 20 centimeters to 40 centimeters at a constant speed, remain at rest, and then go backwards, negative slope, okay, backwards down line to 30 centimeters, and then remain at rest. So let's see what it looks like. So, forward to 20, at rest. Forward to 40, at rest. Backwards to 30, at rest. All right, I'm going to do it one more time just so you get the feel of it. I'm going to draw along, if you haven't looked at my little pointer, I'm going to draw along the graph with where we're at. So starting at 0, constant speed, to 20 at rest. Constant speed to 40 at rest. Backwards to 30 and at rest. Notice that my little mouse didn't stop moving because even though the object stopped moving, time did not. Time keeps going forward. So that's one of the little tricky pieces that when you start to think about distance time graphs, really remembering that time keeps going even if your object doesn't. So let's talk about how we'll write this. So for our example, we could say the toy car started moving at 0 centimeters forward with a constant speed, remained at rest, and then went forward to 40 centimeters at a constant speed, remained at rest, then went backwards at a constant speed of 30 centimeters and remained at rest. That's kind of a mouthful, right, but I'll say it one more time. The toy car went forward at a constant speed to 20 centimeters, then remained at rest. Then it went forward at a constant speed again to 40 centimeters and remained at rest. And then the toy car went backwards to 30 centimeters at a constant speed and remained at rest. Take a minute to jot that down. The last thing, that was a very long explanation, but the last thing that we can add here is talking about when we're graphing, adding those math terms back in so we make graphing easier for us. These graphs have multiple slopes. So we notice that there is a slope here that we could calculate, right? Up 2 over 1. There's a slope here we could calculate, slope of 0. A slope here we could calculate, up 2 over 1. Again, 0. Down 1 over 1. Okay. And then finally 0 again. So a hybrid graph is going to have multiple slopes because it's showing you multiple kinds of movement. And I almost forgot to show you this, but this again is my final notes on that section as well. So hybrid notes, if you need it, again, pause it here for yourself. Otherwise, good work today. Okay, so due to how long this video has already been and the amount of notes that you're taking, I'm going to go ahead and scratch the practice problem for today. We'll go ahead and do a couple examples. I'll do a live example in class, or excuse me, on WebEx, and then as well I'll have a video recorded of an example for you guys to do on, I think, Monday. We'll start that, okay? So we'll probably do a couple practice problems together on Monday, as well as some that you can try on your own and submit to Google Classroom. As for today, go ahead and take a picture of those notes with those wonderful colors if you have them, and just go ahead and upload that to Google Classroom just as your check-in, saying that you're caught up. It also gives me a pretty good idea of where everyone is at. If you could comment on a scale in Google Classroom in the little comment feature, on a scale of 1 to 5, how well you feel you're understanding motion graphs. 1 meaning I'm really not understanding it. 5 meaning I really think I got this. That would be great feedback for me to let me know what I need to do to prepare us for Monday.